The final power cycle that we're going to consider in this course is the Brayton cycle. So the Brayton cycle is a gas power cycle. So first of all, let's remember what a power cycle is. A power cycle is a machine that converts heat into work. So this is the same as a heat engine. Heat engine, power cycle means the same thing. So the Rankine cycle was a vapor power cycle. The Brayton cycle is a gas power cycle. So the main difference is that the working fluid is an ideal gas instead of water. Many of the components, as we're going to see, are very similar, but the working fluid is an ideal gas. Now, at the beginning of the course, we introduced a gas turbine as one of the examples of a thermodynamic system. So let's just remember how a gas turbine works. So first of all, we have air here entering a compressor, where it's compressed up to a higher pressure, and the temperature will also increase as that happens. Then after the compressor, heat is added in the combustion chamber, and then the hot products of combustion go through the turbine to produce work. That work goes two places. A portion of the work produced by the turbine is used to run the compressor, and we show that schematically here just by having them mounted on a common shaft. But it produces a lot more work than is required to run the compressor, so that extra work is available in the surroundings here in order to run whatever piece of equipment we want. Typically that would be a generator to generate electricity. And then the gases leave the turbine and go into the atmosphere. So that was a gas turbine that we introduced at the beginning of the course. And this gas turbine is in fact a Brayton cycle. We didn't give it the name at the time, but we're going to go back to gas turbines now and study them in more detail in the context of the Brayton cycle. So we need to realize that in a real gas turbine, the way that heat is added is by adding fuel, so we get a fuel-air mixture and we actually burn it in the combustion chamber. So that's the mechanism by which heat is added in an actual gas turbine. So through the compressor, the working substance is air, but through the turbine, it's the products of combustion. So this is primarily water vapor, CO2, and nitrogen, but there are some other trace gases in there as well. So the working fluid is actually different in the compressor and the turbine because of the combustion. And then after the turbine, the hot exhaust gas is discharged directly to the environment. So this is complicated by the change in chemical composition that happens in the combustion chamber. Now in this course, we're not going to consider combustion. We're going to save that for your fourth year thermodynamics course. But instead, we're going to look at a standard Brayton cycle. So the first one we're going to look at is called the air standard Brayton cycle. And you'll see the initials ASBC to refer to the air standard Brayton cycle. So the air standard Brayton cycle makes a couple of changes from the real gas turbine. First of all is the working fluid is air all the way through. So we don't have to worry about a change in chemical composition. We have lots of experience now doing energy balances on components where air is the working fluid, and we'll be able to use that as we analyze Brayton cycles. So air is the working fluid in the turbine as well as in the compressor. So that basically means that we're getting rid of the combustion chamber and replacing it with a heat exchanger. And we'll see that when we redraw the system here in a moment. The other thing we're going to do is add a second heat exchanger to complete the cycle. Now remember, in an actual gas turbine, the exhaust gases just exit to the atmosphere and the compressor draws fresh air in from the surroundings. Well, we're going to close that loop so this becomes a closed cycle. So we see that here. This is our air standard Brayton cycle. The compressor and the turbine, there's been no changes there really, except that air is the working fluid in the turbine. Up here, instead of having a combustion chamber, we're just adding heat from the surroundings. And down here, we've closed the cycle from 4 to 1 with a second heat exchanger where we're rejecting heat to the surroundings. So this is the air standard Brayton cycle. And by analyzing the air standard Brayton cycle, we can learn a lot about a gas turbine cycle. Now, just like the Rankine cycle, the main property diagram we'll be using to talk about the performance of a Brayton cycle is a TS diagram. So we have temperature on the vertical axis and entropy on the horizontal axis. Now, unlike the Rankine cycle, we don't have to worry about showing the gas-liquid region on here because an ideal gas is our working fluid now. but we do need to know what lines of constant pressure look like. So a line of constant pressure for an ideal gas is going to be a line angled up and to the right like this. So you'll notice it has a little bit of a curve to it. It's getting steeper as we move over to the right. So that's what a line of constant pressure looks like on a TS diagram. And this is very similar to the line of constant pressure in the superheated region, because in the superheated region we're starting to get away from the liquid vapor region, so it starts to look like an ideal gas. So that's a line of constant pressure at a low pressure. In other words, the low pressure in the cycle, the inlet to the compressor and the exit from the turbine. So typically in an actual application this would be atmospheric pressure. And then up in the combustion chamber, or up in the heat exchanger where we're adding heat, we have a higher pressure. So those are lines of constant pressure on a TS diagram. Now the cycle itself, we're beginning with an ideal cycle. And remember, an ideal refrigeration system and an ideal Rankine cycle meant that the compressors and turbines were all 100% efficient. Well, it means the same thing here. So an ideal Brayton cycle will have an isentropic compressor and an isentropic turbine. So the isentropic compressor is a vertical line going from low pressure, so that's point 1, up to point 2. So that's the first of the 4 processes in our standard Brayton cycle. Then we add heat, and we're adding heat at constant pressure, so we're going up along this line, up here to point 3. So that's the inlet of the turbine. And then the isentropic turbine, we drop straight down to the exit of the turbine right here. So again, isentropic, so it's a vertical line on the TS diagram. Then finally, that second heat exchanger we added takes us from 4 back to 1. So heat is removed as we go from 4 back to 1. So because we've added this second heat exchanger, we actually have a closed cycle, whereas the real gas turbine is not a closed cycle. Just a reminder here of what that word ideal means. An ideal air standard Brayton cycle means that S1 and S2 are equal, and S3 and S4 are equal. Now we're going to apply the first law to some of these components. So we would be starting with the complete first law for our open system, because we're going to analyze each of these components in turn. Steady state is being assumed. No kinetic or potential energy changes, and of course, depending on which type of component we're looking at, either work or heat transfer will also be 0. So when we apply the first law to the heat exchanger, or to the combustion chamber, this is really the heat exchanger that replaced the combustion chamber, we see that the rate of heat input, Q dot in, is the mass flow rate times H3 minus H2. And table A22 will be used for those enthalpies because air is the working fluid. The mass flow rate here really determines the size of this Brayton cycle. So the temperatures at the inlet and the exit of the heat exchanger are going to determine the enthalpy change. But whether it's a small Brayton cycle or a large Brayton cycle, that's determined by the mass flow rate through it. The rate of heat transfer would scale with that mass flow rate. The compressor work requirements will be the mass flow rate times H1 minus H2. And realize these mass flow rates are the same in this simple Brayton cycle. And finally, the turbine work produced is mass flow rate times H3 minus H4. So all of these enthalpy values will be coming from table A22. The net work will be the sum of the compressor work and the turbine work. And the thermal efficiency of the Brayton cycle is the same as it is for a Rankine cycle. It would be the net work divided by the heat input. There's an extra parameter that we're going to introduce now that is actually also used for the Rankine cycle, but we didn't introduce it there because it's not as important in the Rankine cycle, and that's called the back work ratio. So this BWR is the back work ratio. Now what is the back work ratio? Well, if we look at its definition here, we can see. So the turbine produces work, and a portion of that work has to go back and run the compressor, if you remember how the components are configured. So the back work ratio is how much of the work produced by the turbine is used by the compressor. So it's the compressor work divided by the turbine work. And we put an absolute value on the compressor work because it's a negative number, because it's work input into the system. So W dot C divided by W dot T, the magnitude of that is the back work ratio. And the back work ratio for a gas turbine is actually quite high. We'll see when we start doing examples later on, but it's 30 or 40%. So a very large portion of the work produced by the turbine is actually required just to run the cycle. A Rankine cycle, that's very different. Remember, the way the working fluid is pressurized in a Rankine cycle is with a liquid pump. And a liquid pump actually requires very little work in order to pressurize the working fluid up to the steam generator pressure. So the back work ratio in a Rankine cycle would be of order 1% or so, whereas in a Brayton cycle it's 30 or 40% at least. So the other way we can do this, of course, is on a per unit mass basis as well. As long as we make sure we're doing the same thing in the numerator and the denominator, we can calculate the back work ratio from powers or from work transfers per unit mass. So everything we've talked about so far is the air standard Brayton cycle. We want to go one step further in our simplification here and talk about a cold air standard Brayton cycle. So we've tagged an extra word on the front and an extra letter on the front of the acronym. So what is a cold air standard Brayton cycle? Well, it's the same components. We still have the same four basic components. Air is still the working fluid. But the difference now is that we're going to go one extra level of simplification, and we're going to calculate the changes in enthalpy from changes in temperature and the specific heat at constant pressure. So we'll be saying delta H is Cp delta T. And this will allow us to simplify the expressions a little bit and come up with a very important relationship for the efficiency of a Brayton cycle. So if we're assuming Cp is constant, then that means we're also assuming the ratio of specific heats is constant. So we'll be making those additional assumptions on the properties of the working fluid for a cold air standard Brayton cycle. So I want to say a little bit more about the isobars for an ideal gas on a TS diagram. It's important to realize that as we go to the right on this diagram, so as entropy increases, these lines get steeper and they diverge. They get further and further apart. And that's really important because if we take a look at the compressor work, which is down here, and the turbine work, which is up here, for a cold air standard Brayton cycle, the length of those lines is directly proportional to the amount of work produced or the work required. Because remember, the delta H is now Cp delta T. So the length of those lines scales directly to the work. So if these two lines of constant pressure were just parallel and straight, then a vertical line here and a vertical line here would have the same length. And our back work ratio would be 100%, which means all the work produced by the turbine is required by the compressor, and there would be no work left for output to be used in the surroundings. So it's very important that these both curve and get steeper as we go up, so that a vertical line, the vertical distance between them, gets longer as we move to the right. So that's a very important feature of these isobars, or a gas turbine simply would not work. So now I want to talk about the thermal efficiency, and we've got a little sketch of our basic cycle down here to follow along. Well, remember, thermal efficiency is the net work divided by the Q added. So we're concerned with the amount of heat added as we go from 2 to 3, and the net work, including the compressor work and the turbine work. So for our cycle, we can write that as changes in enthalpy. And so this is still valid for air standard cycle as well, because we're expressing the work and heat transfers as enthalpy changes. So to look at the numerator here, 3 to 4, that's the turbine work. And then we add to that 1 to 2, which is the compressor work. So that's the net work in the numerator. And then in the denominator is the heat added in the combustion chamber or in the high temperature heat exchanger. So that's the H from 3 to 2. So that's our thermal efficiency. Well, if we're going to stick with an air standard Brayton cycle, then we can get all of these enthalpy values from A22, assuming we know the temperatures at all 4 of those points. Now, however, if we go to a cold air standard Brayton cycle, we can make some further simplifications to this so that we don't have to go to table A22 to figure out the efficiency of the cycle. And we can better see what are the most important parameters that determine the efficiency of the Brayton cycle. So going back to our expression for efficiency, we're just replacing each of the delta H's by Cp delta T. And since Cp is constant, it can cancel out of this relationship. And so we just get an expression for efficiency, which is based on the temperature at the 4 points in the cycle. Now, this is still a long way from really clarifying what the most important parameters are for determining the efficiency of the Brayton cycle, but we're going to work with this expression a little while and come up with the most important thing that determines the efficiency of this cycle. First thing I'm going to do is just rearrange temperatures in the numerator. So all that I've done here is taken T4 and T2 and they've traded places. So it's still exactly the same value on the top, just T4 and T2 have traded places. Now realize that that makes these two terms the same when we do that. So we can now write that expression as the efficiency is equal to 1 minus T4 minus T1 over T3 minus T2. So this is just starting to get this into a form that'll show us the most important parameters for determining efficiency. Now that still involves all four of these temperatures, so that's not particularly enlightening yet. But in this next step, we factor out of the numerator T1, so that's shown here, and we factor out of the denominator T2, so that's shown here, and then the portion in parentheses is what's required to get back to this. So T1 multiplied by this just gives T4 minus T1, and T2 multiplied by this gives T3 minus T2. So now what we want to do is take a look at some of these temperature ratios and see if we can express some of those temperature ratios in terms of these pressures. That's what we're aiming for here, is to get our expression for efficiency in terms of these pressures. Well, if we look at this process from 1 to 2, remember that's our compressor, and this is an ideal cycle, so that's an isentropic compressor. And remember, an isentropic process with an ideal gas with constant specific heats is a polytropic process, and that follows PV to the K is a constant. Now we also know that we can get rid of the V's in that expression and write them as P's instead, and that gives us this equation that we've used many times, that the temperature ratio is equal to the pressure ratio times K minus 1 over K. So these temperature ratios we can write in terms of pressure, and that's what we're going to do. So looking at the compressor, that gives us a relationship for T2 over T1. Well, we can do the same thing for the turbine. The turbine is also isentropic, so T4 over T3 is P4 over P3, K minus 1 over K. So we have these expressions for temperature ratios based on the fact that the compressor and the turbine are isentropic. Now realize that P4 over P3 is actually equal to P1 over P2, right? P4 over P3 equals P1 over P2 because P1 and P4 are the same and P2 and P3 are the same. So I can rewrite this like that. Now notice these two things are almost exactly the same. One is just the inverse of the other. So what I'm doing here is getting a relationship between these two temperature ratios that I can use to simplify this. So that means T2 over T1 is equal to the inverse of T4 over T3. So that's what we'll say. T1 over T2 equals T4 over T3. We can conclude that from that previous slide. Well, if I just cross multiply these, this also means that T4 over T1 is equal to T3 over T2. So that means we go back to our efficiency expression. This stuff is all just equal to 1 because these two ratios are the same as each other. They have to be because the compressor and the turbine are operating between the same two pressures. So we can cancel all of that out and we get that the efficiency is just T1 over T2. So remember what this is? That's the temperature at the inlet to the compressor, the temperature at the exit of the compressor. So in terms of temperatures, those are the only two temperatures that matter in determining the thermal efficiency of this cycle, the temperature ratio across the compressor. Now there is one last step here to get this into its more conventional form. Typically we don't write this expression for thermal efficiency in terms of temperatures. It's much more common to write it in terms of pressures. So the last thing we'll do here is substitute for that temperature ratio, P2 over P1, 1 minus K over K. So again, that's the isentropic relationship for the compressor being used. So this shows us the most important expression for efficiency for a Brayton cycle. Essentially, the efficiency of the Brayton cycle is dependent on the pressure ratio across the compressor, and this is called the compression ratio. So the most important parameter determining the efficiency of a gas turbine is its compression ratio, the ratio between the pressure in the combustion chamber and the pressure entering the compressor, which is typically atmospheric pressure. Now we want to continue talking about efficiency, but in the context of the TS diagram. So in an actual gas turbine, the low pressure is always going to be atmospheric pressure because they're drawing air into the compressor from the surroundings and discharging combustion products from the turbine into the surroundings. So P atmosphere is always going to be the low pressure in the system. Also, point 1, the inlet to the compressor, is essentially fixed. That's atmospheric conditions, whatever they happen to be on that day. So there's really very, very little we can do about the location of point 1 in the cycle. So the basic Brayton cycle looks like this. 1 to 2, the compressor. 2 to 3, heat added in the combustion chamber. Then 3 to 4 is the turbine. So we want to revisit the thermal efficiency on the TS diagram. Well, we learned when we looked at the equations that the ratio between these two pressures is the thing that determines the efficiency, and the higher that ratio gets, the higher the efficiency is. Well, P atmosphere is fixed, so we can't increase the efficiency by dropping that P atmosphere down. We don't have control over that. So the only thing we can do to increase the efficiency is increase that pressure. So we want to take the high pressure and make it as large as possible to increase the efficiency. Well, the other thing we want to remember about a TS diagram is that the net work produced by the cycle is the area enclosed by the TS diagram. So that area is proportional to the net work. And here it's written as the net work on a per unit mass basis. So to get the net power, we would just have to multiply that by the mass flow rate through this particular gas turbine. So that area is proportional to the net work, and that's a very useful thing to remember as we spend the next little while here exploring how changes in operating parameters affect the efficiency and the net work output. So we're going to be talking about those two performance parameters, the efficiency of the cycle and the net work that it produces. Ideally, we would like both of those to be as large as possible. So one thing that we can do to increase the work is to take this vertical line and move it further to the right. So we can certainly see that that would increase the area enclosed in the TS diagram, but also as we take that turbine process and move it further to the right, that line gets longer because these lines are diverging and also because they're getting steeper, so the vertical distance between the two of them increases. So moving this line to the right is going to increase the work output. Notice it's not going to do anything to the efficiency because the efficiency only depends on where this pressure is. So moving that to the right increases the work output. Well, how do we move that to the right? Well, we add more heat in the combustion chamber or in the high pressure heat exchanger. So we just continue adding more heat. Instead of stopping here, we move point 3 further and further and further up this line by adding more and more heat at the heat input heat exchanger. Well, the problem with that is that there's only a certain amount of heat we can add. And the reason for that is that as we go up this line, of course, the temperature is increasing. And we can't let the temperature increase so far that the hot combustion gases are going to melt the turbine blades. So the temperature capabilities of the turbine blades is one of the most important characteristics of a gas turbine or a jet engine. And a lot of research has gone into making turbine blades that are able to withstand higher and higher temperatures. Well, for current materials and turbine blade designs, about the maximum that we can let this temperature get is 1700 Kelvin. So I'm showing a 1700 K line here, and we cannot let 0.3 get above that line or the turbine blades will melt. So we can increase the amount of heat added in the combustion chamber up to a point. And so this shows sort of the maximum we would be able to achieve. So we've increased the heat added in the combustion chamber to increase the net work of this cycle. Now let's say that we wanted to increase the efficiency of the cycle as well, which we also do. Well, we would want to take this pressure and move it up. Well, realize that as we take that line of constant pressure, and move it up, if we still add the same amount of heat, we're going to go to too high a temperature here. This 0.3 is going to move up as well. So we can't do that. As we increase this pressure, we are going to have to reduce the amount of heat we add in this heat exchanger in order to keep 0.3 below 1700 K. So this just shows that. This shows an increase in the efficiency because we've increased our pressure in the combustion chamber up to this value. This dotted line shows where it used to be. So we've increased that efficiency. Notice we've had to cut way back on the amount of heat added because we need to keep 0.3 below our maximum temperature, whatever that happens to be. And so the work is actually now reducing. So the area is reducing because we have to restrict the amount of heat added as we go to higher and higher compression ratios. So what's happening here is the air is starting off down at this temperature. We can't let it go higher than this. Well, there's two things that cause the temperature of the air to increase. There's the temperature increase because we're compressing it in the compressor, and then there's the temperature increase because we're adding heat in the combustion chamber. So the more we compress the air, the higher the temperature increase across the compressor, and the smaller the remaining amount of temperature increase is before we get to that maximum allowable temperature. So we can increase the efficiency of this heat engine, but we have to reduce the work in order to make that a practical working gas turbine. So when T2 equals T3, the work is 0. So that just means if we increase this pressure so far that these two temperatures become the same, then of course the work is 0 because that area will totally disappear, totally collapse. So when T2 equals T3, the work is 0. Well, also, when P1 equals P2, the work is 0. So what is that talking about? Just going back. Well, that's if we were to do the opposite thing. If we were to take our combustion chamber pressure and reduce it, of course, then we could add more and more heat, just be the opposite of what we were just looking at. But eventually, this area would go to 0 because our high pressure would be down here. So when T2 equals T3, the work is 0 because we've flattened this area trapped by the cycle by making it narrower and narrower. But when P1 equals P2, the work is 0 because we've flattened it out. So there's those two extremes that give 0 work. T2 equals T3 and P1 equals P2. Both of those give 0 work. Well, that means that there's somewhere in between when the work is a maximum. And we won't go through this development, but it turns out that if our pressure ratio is equal to this, so the temperature ratio raised to the power k over 2 to the k minus 1, then we get maximum work output. So remember what T1 and T3 are. T1 is atmospheric temperature, and T3 is the maximum allowable temperature based on the materials of the turbine blades. So those are both parameters of operating conditions, T1, and the materials you're using in the machine. So this tells us the maximum possible work output that we can get for those particular temperature limits, and it would occur at a compression ratio given by this equation. So recall that the actual power of the engine, W dot, is the mass flow rate times the work per unit mass. So a large work per unit mass allows a small mass flow rate to get the same power output. So it allows for a smaller engine, a lighter, smaller, more efficient engine. Next, we want to talk about the concept of reheat. So notice up to this point, we've only had the 4 basic components in this air standard Brayton cycle: compressor, combustion chamber, turbine, and then the second fictitious heat exchanger to close the loop. Now we also introduced this idea that there is a maximum temperature that we can allow, so we can't go above whatever the material limitations are of our turbine blades. A way to increase the power output of a Brayton cycle without going above that temperature limit is to use a reheater. And this is exactly the same concept as in a Rankine cycle, and we're using it for exactly the same purpose, to keep the temperatures from going too high. So to increase the power output without going above some maximum temperature limit that is governed by the materials we're using. Well, in a Brayton cycle, the reheater turns this single-stage turbine into a two-stage turbine, the same as it did in a Rankine cycle. So if we show an intermediate pressure now between our atmospheric pressure here and the pressure in our combustion chamber, we have some intermediate pressure where the reheater is going to operate at. We now have a high-pressure turbine stage going from the combustion chamber pressure to the reheater pressure. And then we add some heat, so that's our stage 1 turbine. This is the reheater, so we're adding heat at constant pressure, taking us back up to higher and higher temperatures. And the maximum we could go to, again, is where this red line is, right there. So that would be the exit of the reheater, and that's when stage 2 of the turbine would take over. So this is the first stage of the turbine, the reheater, and the second stage of the turbine. So we can see that the increased work output of this cycle is this area here, because that's the increased area enclosed by the entire cycle now. So the work increase is fairly evident on a TS diagram as a result of adding the reheater. So for the case of a reheater, the increase in net work is due to an increase in the turbine work. Now Brayton cycles can also make use of intercoolers, and so we want to talk about that now. And it's almost exactly the same concept, but happening at the compressor instead of at the turbine. So we add an intermediate heat exchanger called an intercooler at some pressure between the inlet atmospheric pressure and the combustion chamber pressure. We compress from atmospheric pressure up to that intermediate pressure. Then we remove heat, or we cool off that air that has been partially compressed down to this point. Then it leaves the intercooler and enters the second stage of the compressor that takes us from that point up to the combustion chamber pressure. So it's now a two-stage compressor, stage 1 and stage 2, with an intercooler in between. And so this area now is the amount of work increase, but as a result of decreasing the compressor work. So with an intercooler, we can compress the gas up to the combustion chamber pressure with significantly less work. And how much less work? Well, that area right there tells us exactly how much less work it takes. And so that contributes to an increase in the net power. Notice the intercooler hasn't done anything to the turbine, just like the reheater didn't do anything to the compressor. So both reheat and intercooling both serve to increase the net power output of this cycle without going above our maximum temperature limitations. The next concept we want to talk about is also one that we talked about in the Rankine cycle, and that is regeneration. So we're going back to our basic cycle here, so we don't have any reheat or intercooling, just our basic 4 components, and we want to show what regeneration is in a Brayton cycle. Well, the first thing to notice is that the temperature at point 4 is typically higher than the temperature at point 1. So let's remember what those temperatures are. Point 4 is the exit of the turbine. So in an actual gas turbine, that would be the gases coming out of the turbine just being released into atmosphere. Point 2 is the exit of the compressor, or the inlet to the combustion chamber. So point 2 is when we're going to start adding heat through combustion typically to get up to the turbine inlet condition. Well, the key thing here is that if T4 is bigger than T2, which it is in this illustration, then we can use some of the waste heat in these exhaust gases here to preheat the air before it goes into the combustion chamber. So between the exit of the compressor and the inlet of the combustion chamber, we can use the waste heat from here to preheat that air. And that means that we won't have to supply as much energy in the combustion chamber. So regeneration will increase the efficiency of this cycle because it'll reduce the amount of heat we need to supply from outside. So that's what regeneration is. And that's exactly the same thing as it was in the Rankine cycle. So we'll see how this works in a Brayton cycle. So we're using the exhaust gases to preheat the combustion air. So the way this is done in terms of the layout of components, we still have the four basic components. We have a compressor, we have a combustion chamber, and a turbine. And the thing we've added now is a regenerator. So the regenerator is a heat exchanger, and it has two separate streams going through it. The outlet of the compressor goes in the cold side and comes out here heading to the combustion chamber. And the exhaust gases from the turbine are the other inlet, and they pass through and give up heat and then finally are exhausted to the surroundings at point 6. So these gases are hotter than these gases, and that's what allows heat to transfer in that direction in the regenerator, and it means that we can preheat this air from there up to a higher temperature here before it goes into the combustion chamber, and that means we need to add less energy in the combustion chamber. So that's how our regenerator will increase the efficiency of this machine. The performance parameter that we need to introduce here for a regenerator is called the regenerator effectiveness. Notice this is not an efficiency. You'll learn a lot more about this in third year when you take heat exchanger design, but we don't quantify the performance of a heat exchanger with an efficiency. Instead, the proper word is effectiveness, and we're going to introduce the regenerator effectiveness here. So the symbol that we're going to be using for effectiveness is an epsilon. So this stands for the effectiveness of the regenerator, and it's defined as the actual enthalpy change. So that's the enthalpy change as the compressed air goes from 2 to 3, divided by the maximum possible enthalpy change. And so we'll be talking about what that is as we go forward here. So in terms of enthalpies and state points on our little sketch over here, the actual enthalpy change is H3 minus H2. And notice that'll be a positive number. It'll be warming that air up a little bit. So H3 minus H2 is the enthalpy increase that it actually was able to produce. Now, what is the maximum possible enthalpy change? Well, notice that of these four temperatures here, the two inlets, T2 and T5, and the two exits, T3 and T6, the highest temperature of all of those is T5. So that's the hot gases coming in here. The very, very most a regenerator could possibly do is increase the temperature at this exit up to T5. There's no way it can make the temperature higher than that because heat does not flow in that direction. So the maximum possible temperature coming out point 3 would be T5. So essentially in the denominator here, we've just replaced H3 with H5. H5 minus H2 is the maximum possible enthalpy change that we could produce. So this is the regenerator effectiveness, and that's a performance parameter that tells us how good the regenerator is. Higher that is, the better. So going back to our thermal efficiency, we've just revisited the expression for thermal efficiency based on the enthalpy changes in the compressor, the turbine, and the combustion chamber. So a regenerator is essentially changing this. It's changing that number, and that's the only difference in this efficiency expression as a result of the regenerator. So it's making it so the denominator is smaller, and so the efficiency will increase because we have to add less heat in the combustion chamber now. Next, I want to look at the combined effect of regeneration with reheat and intercooling, because there's a very important connection between regeneration, reheat, and intercooling. So here we're looking at a cycle that doesn't have any reheat or intercooling, just the four basic components again, and the difference in the temperature between the exit of the turbine and the exit of the compressor is our potential for regeneration. So the bigger that temperature difference is, the more potential we have for regeneration. And so we would like that temperature difference to be larger. Well, realize that a reheater and an intercooler are going to do exactly that for us, and we'll illustrate that here next. So anything we can do to take this point and move it down to the left, so in other words, cool it off, or anything we can do to take this point and move it up and to the right is going to increase that potential for regeneration. So that's what we want to do. If we want to make the regenerator more and more effective, we want to increase that temperature difference as much as possible. So that's exactly what a reheater and an intercooler do. So if we revisit our reheater, the effect of the reheater is to move this point from there to there, and the effect of the intercooler is to move this point from there to there. So our potential for regeneration used to be that, but with the reheater and the intercooler operating, it's increased up to that. So that's a very important benefit of intercooling and reheating, is to increase the potential for regeneration by increasing that temperature difference significantly. The last topic that we're going to address for a Brayton cycle is the effect of irreversibilities. All of the compressors and turbines that we've shown so far have been isentropic. Well, remember that an isentropic compressor is a vertical line on a TS diagram. So as we go from that point to that point, that vertical distance is proportional to our isentropic work, WCS. But the real compressor will drift off to the right as the compression progresses. So that means the actual work is larger than the isentropic work. So that brings us back to the expression for the isentropic efficiency, and that's the isentropic work divided by the real work. And we can see that in this illustration, that the real work is larger than the isentropic work. Same thing happens over on the turbine side. The vertical distance between those 2 points is the work that the isentropic turbine would produce, but the real turbine will drift off to the right, and therefore the real work will be less than the isentropic work. So the isentropic efficiency of the turbine is the real work divided by the isentropic work. So notice these are inverted with respect to each other, but if we remember this little diagram and we remember that the efficiency is always less than 1, we can figure out which way these are. So the effect of irreversibilities on the Brayton cycle is certainly to decrease the efficiency of the cycle.